All right, everyone. Hi, this is a lecture for Chapter 5.7 and 5.8. We're going to cover active and passive transport. This corresponds with pages 90 through 93 of your textbook. And in this lesson, we're going to go over all the very many ways your cell obtains or removes materials by moving things across its cell membrane. So we're going to go into all the different methodologies that occurs with. So generally speaking, we're going to be talking about what's known as passive transport in a little bit of detail, but a lot of it we've covered in the last lecture since it does involve just diffusion and osmosis, but there's something else called facilitated diffusion. And then we're going to be talking a lot about active transport. So in terms of movement of things, we just want to remind ourselves that when we say things are moved with the flow of the universe, with the way things naturally move from high to low concentration gradients, we tend to say it's going down the concentration gradient or going with the concentration gradient. If we're saying material is going against the flow of the universe, instead of going from high to low, it's going from low to high, then in this case, we say it's going against the concentration gradient, and sometimes you're going to hear the term it's going up the concentration gradient because you're kind of going uphill. You're putting more energy into it by going against the grain. All right, so our three types of passive transport we have, things that go with the flow of the universe, but maybe with a little bit of assistance, is osmosis and diffusion, and finally facilitated diffusion. While active transport is actively using energy to go against what's naturally may occur without assistance. In this case, there's something called primary active transport, which we're going to get into, as well as endocytosis and exocytosis. All right, so passive transport is just allowing diffusion from high concentration gradients to low concentration gradients, going down or with a concentration gradient. You don't need energy. You may need a transport protein, though, because there is a limited amount of material that can cross the membrane. You may need a protein that allows for diffusion. So sometimes you have something called what's known as a channel protein that allows things to move across. And you may also use what's known as a carrier protein. So a carrier protein is a protein that can kind of like swing and manipulate itself, so it allows transport across a space, while a channel protein is sort of like, imagine an open tunnel. It's just a straight open hole that only materials that can fit through can get through it. So in this case, going back to this diagram drawing I made a while ago in chapter 4.3, that's why I had two types of transport proteins. And you can actually kind of see it in the image with this passive transport protein, which is actually a channel protein. Notice there's a hole drilled through it. You're seeing materials go from a higher concentration to a lower concentration, and you don't see the use of ATP. On the same image, you see a transport protein that says active transport protein, and you'll see ATP being used. And that's because you're noticing this material is going from a low concentration to a high concentration. And that's why I was using it. Typically, this protein might be called a pump protein or might be called an active carrier protein, but that's just the basics of that. Okay, so passive transport involving diffusion, we've already talked about two types in the previous lecture, so I'm not going to spend a lot of time with that. You should know that diffusion is passive transport, doesn't need energy. It's just the material flowing and spreading out as even as possible, while osmosis is the movement of water diffusion across a membrane, because water can pass through a membrane using its aquaporins that are available to it. But in this case, it's going to move towards the saltier or more solute-filled side to help kind of balance both sides out, because the side with more solutes also typically has less water. Now, there's another type of passive transport called facilitated diffusion, and I consider this like a doggy door. If you have a doggy door or a cat door in the backyard of your house, then you know that you don't really control which way your dog or cat moves, but it gives them the opportunity to move either way depending on their mood. Okay, so it's like a little doorway built into the membrane that allows things that can fit through that doorway to pass through. You can usually sometimes make these proteins or these transport proteins pretty specific, especially if you use what's known as a carrier protein, which can really specifically bind to something and only let that one thing across. Or you can just kind of open a little bit of a doorway and just say only ionic material can pass this, or only XYZ material can pass this, and that's called a channel protein. But either way, if you have that little doggy door opening in your membrane, then you're allowed to do just normal diffusion. So you're going to use facilitated diffusion for materials that don't naturally pass through the membrane, i.e. charged material. So polar material, ionic substances, things like that can't pass through the membrane without help, they're going to get through. However, they have to fit through a transport protein, which means that it can't be a massive amount of stuff and it can't be huge molecules, huge macromolecules that pass through. So typically the material that passes through is pretty small. Ions, small molecules, and monomers, but nothing larger than that is used with this. If you want to transport large amounts of materials, then you're going to probably need active transport, because you need active energy to help manipulate the membrane to widen large enough to take in that material. And I shouldn't use the word widen large enough, but like go in such a way that can take in such a huge material. All right, so facilitated diffusion, because you need to have that little doggy door, there are two types of doggy doors you can use. So one of them is a channel protein. So a channel protein is basically a tunnel, and I'll play this video here even though you can't really hear the audio. But a channel protein really works as a tunnel that allows small materials through that can fit through. But if you really wanted only one specific type of molecule to get through, then what you actually want is a channel protein, which will only swing open if the right material binds that channel protein, and then it will alter its shape to allow that substance to pass through. So channel proteins, like I said, open tunnel, you can't really control which way it's going to go through, but it's open for material to pass through. With a carrier protein, though, this is very useful for very specific molecules that you want to pass through. All right. Now, channel proteins are always, because it's a tunnel, is always passive, while a carrier protein can actually be passive or active. So it's a little hard to describe. There's another video of it over here. But I like to think of a channel protein as sort of like as an open doorway, while a passive carrier protein is a swinging door. And some of you know some doors can only open in one direction versus both directions, and some doors will refuse to like give you access when they're swinging if you don't have the right key code or whatever. And you also know some swinging doors can be active carriers, because they'll only open in one direction and they won't let material go in the opposite direction, and they're using energy to force you through. So it's a carrier door, sometimes that's using energy, or an active energy transport protein that's using energy to force things through in a way that it may not naturally want to go through. I like to think of it as like a really aggressive swinging electric door. Okay, now so for active transport, you can be a carrier protein or you can be something called a pump protein. Both of them act very similarly in that you're using energy to force material through in one direction. And in this case, you don't have to adhere to the concentration gradient. You don't have to go with the concentration gradient. You can go against the concentration gradient. Now, active transport encompasses any type of transport method across the membrane that requires energy and requires membrane proteins. It doesn't necessarily need a transport protein. So if you're transporting a very large amount of molecules, you're going to be using something called endocytosis or exocytosis, which uses vesicles. We'll get into that in a little bit. And that doesn't actually use transport proteins, but it does involve a lot of membrane proteins manipulating to create that kind of transport. Or you may use a transport protein to move materials against the concentration gradient, like I showed you in the previous slide with that pump or active carrier protein. So in this case, your materials are capable of going against the concentration gradient, though you could be going with the concentration gradient. The main thing is you're going in one direction, in one general towards one side, whatever side it is, and it allows the cells to maintain a concentration gradient that's different from the surroundings, so it doesn't have to go with the flow of the universe. It goes, I want it on that side of the cell, and then it just moves it that way. But again, if you're transporting very large materials, those little doggy doors aren't going to be enough, so you're going to need a little bit of energy to manipulate your membrane to allow large-scale transport of material. So even if you're not going against a concentration gradient, just the act of moving such a huge amount of stuff takes a lot of effort by the cell. So these are the three types of active transports which were mentioned earlier. So let's go over the most simple kind. Now, unfortunately, its name is very annoying because it's one of the three types of active transport, and its name is active transport. Yes. So one of the three types of active transport is active transport. But in this case, you're using a transport protein to simply move things in the direction that it wouldn't naturally flow from areas of low concentration to areas of high concentration. All right. So in this case, though, there's the types of proteins that could be used in active transport could be the transport protein, like I showed you earlier for the simple kind of active transport. If it's a pump protein, it's basically a carrier protein, but it's called a pump protein because it literally looks like it's pumping things. It's like that amount of energy it's using is really creating kind of like a forceful pushing motion towards whichever side of the membrane you're trying to move stuff. And then, of course, we'll talk more about the other types of membrane proteins that might be used, but some might be considered like receptor proteins. You might use enzyme proteins. You might use structural proteins in the membrane to help manipulate the membrane in other types of active transport. Okay, so the most annoying named type of active transport is also named active transport, but another name for it is what's known as primary active transport. So it's the use of a transport protein and ATP energy to move material in one direction. Generally speaking, you're going to use this when you're trying to go against the concentration gradient, though you can use it to move things just in a direction a little bit faster than might normally occur with diffusion. So in this case, one of the more famous kinds of active transport is the sodium-potassium pump, which is used by the neurons and muscle cells in your body because it uses it to create this like crazy electrical gradient that allows electricity to help move signals across your body really quickly. You're going to be using active transport whenever you need to transport small materials. The small materials may be ionic, it may be polar, it may be nonpolar, but it's going to be useful for small materials because that's about as large of a hole that the transport protein is capable of making. So I'm just going to show you this picture of the classic sodium-potassium pump. Or video. So in this case with the classic sodium-potassium pump, what actually occurs is it's moving potassium inside and sodium outside the cell. And wow, it's slow, but basically you're going to move 3 sodium ions with energy outside the cell, and then you're going to also use that energy to help move 2 potassium ions into the cell. And eventually what ends up happening is you create this kind of charge gradient where the outside, because you're moving more positive stuff outside than inside, the outside builds more positive than negative inside and just becomes more and more charged. And eventually you can use that system to help manipulate like a really strong impulse, a really strong electrical signal like along a neuron to send information across your body super fast. You'll get into it if you do anatomy or AP Bio. Okay, another type of active transport protein that we talked about, or that we're going to talk about quite a bit, is the proton pump. And this is the big one we're going to be using in our class. You use the proton pump to create this kind of, again, another charge difference gradient by pumping a lot of the hydrogen ion onto one side of the membrane. And that's going to build up a really strong positive side of the membrane and a negative side of the membrane, and then you can manipulate those charges to help crank out a lot of material that you may need. It kind of creates sort of a it just creates kind of a charge differential that's going to become super important, and that's actually going to be covered in our next unit. Okay, now let's talk about large scale movement where you're not simply using an active transport protein. You're not just using a transport protein, but instead you're manipulating your membrane. So in this case, if you want to move a large molecule or large amounts of a molecule, what you're going to be using is a vesicle or vacuole, and you're going to use that vesicle and vacuole, and you're basically going to essentially wrap your membrane around any material you're trying to take in, or sending vesicles to your membrane and then having that vesicle fuse and dump the contents of it outside the cell. And the act of taking your membrane and pinching it off to bring stuff in, or taking vesicles and fusing it and releasing materials, that's going to use a lot of proteins in your membranes to do that active manipulation of the membrane. And it's going to use energy because that takes a lot of work. So that's why it fits the definition of active transport. So there's two types. There's one type called exocytosis for when you want material to exit, and there's another type called endocytosis when you want material to enter the cell. Now for exocytosis, you're using vesicles to transport the membrane and fuse it with the outside membrane, which is going to release its content. While in this case, with you're going to see this happen a lot with secretory cells that make things for the body, because so you have cells in your body that make a lot of stuff your body may need. You have your pancreas cells that make a lot of insulin for your blood to help regulate your sugar. You have cells in your body that help dump hormones into your blood, and they need to make stuff in the cell and then dump it into your blood so that you can get like your adrenaline up, or you may undergo puberty and things like that. So exocytosis is incredibly important for cells that do a secretory function, meaning making stuff and releasing it into the environment. Now endocytosis, and I'll give you another example of excretory, your mucus cells. So making mucus and dumping it on the outside of the cells so it can like slick and protect your body and catch gross stuff. That's thanks to exocytosis, where your cell makes mucus and then the exocytosis process allows it to dump outside of the cell. Now for endocytosis, in this case, we're taking things in. So we're going to be using this whenever we want a cell to suck up stuff, to eat food, or in this case, sometimes to respond to a signal and then take in new material that's just outside of the cell. So in this case, you're going to wrap your membrane around the entering material, and there's three kinds of endocytosis. There's something called cellular eating, where you're just having your cell wrap around a very large solid material and drag it in. You have something called pinocytosis, where it's just wrapping itself around the liquid around the outside of the cell, which hopefully has some solutes you want, and just dragging it inside. So you're sort of, in effect, slurping up a drink from the outside of the cell. And there's a special kind of endocytosis that's called receptor-mediated endocytosis. It's just endocytosis that only takes in stuff once that's very specific to what the cell wants to take in. And you can make it specific by having a receptor protein on the edge of your cell that will trigger the vesicle endocytosis formation only when material specifically binds that receptor. Okay? So these are images of what that looks like. So phagocytosis literally like wraps around the material you want to drag in, and then it's used for digestion usually. And what actually ends up happening is this vesicle often fuses with the lysosome to digest the material that's incoming. Your white blood cells do phagocytosis quite a bit. Pinocytosis is more nonspecific. You're just dragging in material from the outside that's dissolved in liquid, so you're just kind of slurping up a drink of dissolved stuff, and your cell may be using it. And both phagocytosis and pinocytosis could be triggered or caused when a specific receptor binds and says, hey, we should take this material in. But receptor-mediated endocytosis is just saying it's a type of endocytosis that gets triggered when the receptor gets bound. And you could have receptor-mediated phagocytosis and receptor-mediated pinocytosis. But in these instances, what occurs is your receptors must bind to the material you're looking for, and then your cell will only drag in this material when they're like, oh, I have the stuff I want. And they won't drag in material unless they know that this is the stuff they want. And that occurs when you have the material bind the receptors. These are different images. This should say pseudopodiums. You don't even need to know the word pseudopodium. So this is phagocytosis, where you're dragging in large materials into a vacuole, and it's a vacuole, not a vesicle, because the material is so large by default it becomes a temporary vacuole because it's just bigger than your typical vesicle. While if it's smaller material, you're dragging in material that's fairly small, so the bubble around it is also fairly small, so then we just call it a vesicle. And receptor-mediated protein, again, or endocytosis, again, is basically the other two, but it's just ensuring that you don't drag in stuff unless it sticks to your receptors to ensure that the stuff that you're dragging in has what you want. Now, I mentioned receptors in the past and as it relates to COVID-19, and the virus for COVID-19 called SARS-CoV-2 is actually using receptor-mediated endocytosis, but instead it stole the key that your body uses, and it basically, what is that? They faked the key. They made a copy of the key to trick the cell into taking it in through receptor-mediated endocytosis, and it gains entry into the cell by binding what's known as the ACE2 receptor. So the ACE2 receptor is actually a really important receptor in your blood vessels because it helps control damage in your body due to a different type of process in your body. So one of the processes in your body creates inflammation and high blood pressure, which is actually useful when you're trying to fight off diseases and stuff, but can be dangerous if you go into overdrive. It can cause damage in the long run. So the ACE2 receptor actually counters this normal bad response in your body. So a lot of your blood vessels in your body have a lot of ACE2 receptors. So unfortunately, because the virus SARS-CoV-2 has stolen the key that we use for a very important protein we need to help regulate our blood vessels, it now can enter and sneak into all our blood vessels and other cells with the ACE2 receptor, such as the cells in the back of your throat and the cells in your lungs, because your cells in your lungs have a lot of blood vessel lining it too to help bring in oxygen. All right, so here are some simplified cartoony version images of the different types of cell transport we went over. You don't have to draw these in. I just kind of like to show it because it helps students kind of wrap their head around it. So diffusion, you're just letting the material spread out more than it was. Osmosis, the water moves to the side that's a little bit more salty, a little bit more solute to help provide more equality balance in the concentrations on both sides when the material can't pass through, but water can pass through the membrane. While facilitated diffusion is just diffusion, but because the material can't naturally pass through the membrane, it needs a protein, like a carrier protein or a channel protein, to open up to allow diffusion to happen. While in the other case with active transport, you need energy and some kind of active protein, transport protein, to help move things against the concentration gradient for simple active transport of smaller material. But if you're doing large materials where you're either swallowing it, like in endocytosis, you're letting that material enter, or in exocytosis, where you're taking that material and removing it, even though it's not in the picture, because you're doing such large amounts of material, because the membrane has to, and vesicles have to be formed, and the membrane has to be messed around with, you're still ultimately using membrane proteins to help manipulate the membrane and energy to allow that complicated process to occur. All right, so this is a video with lots of resources, so you can play this video over here if you want to know more about membrane transport. And then these are all major resources I know of that are very common for our class that you may want to reference. Crash Course has really good animations if you're a visual learner, but they go through material so quickly. I would recommend Crash Course for after you do notes to just kind of review things. Bozeman Science is kind of a slow, thoughtful, very detailed re-explanation of our class material. So if you just want a different version or way of explaining things, you might want to look at Bozeman Science. While if you're just completely lost and you really don't know what's happening, Amoeba Sisters provides really simplified explanations of materials that may help you out. And finally, I listed Khan Academy. Khan Academy's AP Bio website, while a little bit more advanced than what we go through, often has really thorough, really in-depth explanations and drawings that may help you out when you're learning the material or a little bit confused. Okay, so in summary, these are the things. Passive transport doesn't need energy. It's just allowing diffusion in a normal way, though you may need proteins to help material that can't naturally cross to get across. While in this case with active transport, you need energy and membrane proteins to qualify for active transport. It could be a transport protein, but it doesn't have to be a transport protein. Proteins are involved in the movement of vesicles, and in this case, exocytosis and endocytosis also qualify as active transport, with exocytosis being movement of material out of the cell using vesicles, and endocytosis being the movement of materials into the cell using vesicles. And these were the vocab terms we covered. All right, that covers our lecture. Have a good day.